Our middle-aged star, the Sun, is typically rather normal. But that's not the case with its planets. Mercury is first. It probably lost its outer layers in a catastrophic collision long ago, leaving it with more burned interiors than a fully developed planet. Next, we have Venus and Earth, which are in some ways identical twins, but only one of them is productive. Another little globe is Mars, which unlike Mercury never lost layers and simply stopped expanding. After Mars, there is a large ring of remaining rocks, and then the landscape changes. The next is Jupiter, which is so massive that it resembles a partially roasted sun. Beyond that are three further massive worlds made of gas and ice: Saturn, Uranus, and Neptune. Despite having formed around the same star, from the same material, at around the same time, the four gas giants and the four rocky planets have essentially nothing in common. The 8 planets in the solar system raise the question, why these? Now cast your gaze far beyond the Sun. The majority of stars are home to their own planets. Thousands of these far-off star and planet systems have been discovered by astronomers. But oddly, they haven't yet discovered any that even closely like ours. Consequently, the puzzle has become more challenging. The expanding list of extrasolar planets, observations of far-off planet systems, and even fresh information from within our own solar system don't support previous models of planet formation. It has become clear to planetary scientists that there may not be a unifying theory of the origin of the universe that could account for every planet orbiting every star. Our system indeed originates from a hazy cloud of gas and dust. The cloud imploded under its own gravity to form a new star 4.5 billion years ago, probably prompted by a passing star or the shock wave of a supernova. We don't truly comprehend what transpired next, how things actually turned out. When the Sun first burned, extra gas swirled around it. The planets eventually developed there. This was explained by the minimum mass solar nebula, a simple protoplanetary disk that included enough hydrogen, helium, and heavier elements to form the planets and asteroid belts observed. The 1977 model predicated that planets formed where they are today, first as little planetesimals, then assimilating all the material in their region like locusts eating every leaf in a field. According to a hazy theory put up by astronomers, planetesimals formed because dust particles driven around by the gas would have drifted into piles, much like how wine-shaped sand dunes. According to the traditional hypothesis, planetesimals were dispersed across the solar nebula at random, with a statistical distribution of sizes that followed a power law. The change come from the Atacama Large Submillimeter Array, ALMA, giant radio telescope, made to pick up light from cool, millimeter-sized objects, such as dust flecks surrounding young stars. Beginning in 2013, ALMA produced breathtaking photos of immaculately formed young star systems with potential planets hidden within the hazy disks surrounding the young stars. These disks were once thought of by astronomers as diffuse halos that extended away from the star. However, ALMA revealed disks with deep, dark voids, akin to the rings of Saturn, some with arcs and filaments, and some with spirals, akin to tiny galaxies. The measurements revealed that dust does not evenly distribute throughout the disk, but rather gathers in specific locations, as dust is prone to do, and that is where the earliest planet embryos form. For example, it's likely that some dust congregates at some distance from the star at which water freezes. Some astronomers claim that dust also collects near a condensation line, where silicates condense into droplets rather than vapor. Condensation lines likely create gridlock, slowing the pace of dust fall toward the star and letting it accumulate. Before a radio telescope revealed where dust tends to gather, astronomers were perplexed as to how it could amass quickly enough to become a planet, particularly a big one. The gas surrounding the newborn sun would have dissipated within about 10 million years, which means Jupiter would have had to collect most of it within that time frame. Because of this, Jupiter's core must have formed extremely quickly after the sun's ignition. The issue is that dust would not orbit the sun in clean patterns or drift into large piles due to turbulence, gas pressure, heat, magnetic fields, and other characteristics. In addition, gravity would probably pull any large clumps toward the sun. The Princeton University researchers Andrew Udine and Jeremy Goodman developed a new theory for dust clumps in 2005 that made some progress toward a solution. They contended that a few years after the sun first flared, gas circling the star created headwinds that caused dust to condense into clumps and prevented the clumps from falling into the star. The original dust bunnies eventually shrank under the weight of their own gravity into compact shapes as they grew larger and denser. This concept, known as streaming instability, is now a widely accepted explanation for how millimeter-sized dust particles may transform into enormous rocks so swiftly. The process can produce planetesimals that are around 100 kilometers across when it collides with one another. The origin of much larger worlds like Jupiter, however, has remained a mystery to scientists. A variation on planet growth known as pebble accretion was put forth in 2012 by Anders Johansson and Mikael Lambrechts, both of Lund University in Sweden. They contend that planet embryos the size of the dwarf planet series that form as a result of the streaming instability quickly enlarge. Dust particles and small pebbles would spiral onto these things as a result of gravity and drag in the circumstellar disk, and these atoms would continue to grow quickly, much like a snowball sliding downhill. Many scientists contend that pebble accretion may be occurring in those radio telescope photos, allowing giant planets to develop in the first few million years following the birth of a star. Pebble accretion is now a popular explanation for how gas giant cores are produced. The theory's applicability to the tiny, terrestrial planets close to the sun, however, is debatable. Despite the fact that pebble accretion produces planets relatively well, it doesn't appear to be the sole method. No matter how insatiable our curiosity may be, the birth of a planet takes millennia, whilst our lives are brief. Our sole access to the process is through pictures taken at various moments.